Good evening, or sorry, good afternoon and good morning, everybody. I hope you are having a fantastic day. Here for another honors chemistry lecture. The second I started recording, I realized my glasses were very dirty, but I don't feel like stopping. So, here we go. So, a little more. So I hope all of you are doing well. It's quite late, so I'm going to do my best to keep myself up with a small bag of candy corn and a Pepsi. Today I'd like to jump right into Chapter 3. I know we just did Chapters 1 and 2. I am wary of giving a test or even a quiz while I'm out. I'm going to consider, maybe I'll talk to Dr. Butler and see if he could sit in, if he's free during your class, and administer a quiz. But for now, let's focus on Chapter 3. Chapter 3 is matter and energy. We've already done a bit of classifying matter, I believe. No, hold on. Let me check your classwork. By the way, you can find this PowerPoint to follow along under classwork. Yes, we already did a bit of classification of matter. Okay, that's what I thought. Just needed to make sure. I want to go more into depth on matter in general. So, without further ado, let's get started. Now, I'm still going to, let me enable drawing now. And hold on. Well, you know what? I'll just have to pop out whenever I want to draw. So, we're going to talk about matter and energy. So first off, right, we pretty much already talked about this. Day 1, 2. Everything you can see, at least a physical thing, not including the light, stuff like that, is made of matter. Right? There are many different kinds of matter. So, molecules and atoms. In this picture of a room, we can see molecules of water in this water bottle. We could also zoom in on this golf club, which is likely an aluminum alloy. And we can see atoms. They might be multiples together, but they're all the exact same atom. And I'll get into more of how that is different from a molecule. Oh, never mind. It was zooming in on those little bits. It was zooming in on the carbon fibers. So the graphite. I forgot that I had the label right there. So, a recap on stuff from our first chapter. Matter is defined as anything that occupies space and has mass. Right? Stuff like steel, wood, plastic, that's stuff we can easily see. Other things that are still matter, but are not stuff that we can see, is stuff like air. Stuff like microscopic dust, right? Microscopic organisms. Just because you can't see something doesn't mean that it's not matter. It either just might be in a form that you can't see, like air, but you can still feel air, right? You can feel the resistance against your hand when you move it around. And you might not be able to feel microscopic dust, but that's more just because it's so small it doesn't have an impact on you. Matter often appears smooth and continuous. It's not. Right? This is because matter is composed of atoms. Atoms are something we call submicroscopic. So microscopic would mean you can see it with a microscope, right? Submicroscopic means it is so small you can't see it with a microscope. Atoms are the building blocks of all matter. We have a couple different forms of matter, right? If you have two atoms bonded together, two or more atoms bonded together, you get a molecule. These can be the same atom, right? You can have oxygen and oxygen bonded together to make an oxygen molecule. These have specific geometric arrangements. All molecules of a certain type are the same. So all water molecules have the same shape and the same property, and they are the same size. So even though they're submicroscopic, we can use microscopy, which really isn't using microscopes, as to say, or a traditional microscope, and it's not in the micro range of micrometers. Really, that's where the word comes from. But rather, microscopy is a field which talks about pretty much enabling us to image small things. So when we talk about, the reason I use the phrase here, image atoms and molecules, instead of see them, it's because you're really not seeing them. You're using some sort of thing to detect their presence when you use microscopy. So here's an example of a non-smooth and continuous thing. Look at the top of a soda can, and you can see that it's smooth. Right? You feel it, it's smooth. However, if you were to look down at an atomic level, right, you would see that it's bumpy because all atoms are spherical and they are independent. They're not forming the smooth layer. As a quick side and fun fact for the day, aluminum cans are one of the single greatest feats of engineering of all time. We produce so many aluminum cans every year that to shave even a fraction of a cent off of the cost of making one saves millions, if not billions of dollars. So they have pretty much been perfected. They are strong enough to be able to stack in large amounts. So you can stand on an aluminum can from the top when it's sealed. However, they are vulnerable from the side because they don't get pressure put on them from the side. They are engineered to be as strong as possible while using the slightest bit of material. On top of that, it's actually good to use aluminum. 99.9% of aluminum, no, just 99% of all aluminum is recycled every year because it's really, really hard to make new aluminum, so it's very economical to use it. And it doesn't just get recycled in the way that plastics get thrown out. It really gets recycled, melted down, and remade into something else. So aluminum is a pretty good element. Actually, it used to cost so much that Napoleon had a dining set made of aluminum that he would pull out to brag to people. But anyway. Alright. In addition to, these would be examples of atoms. Each of these atoms is independent, and it might be held together, right? And I won't go into exactly what holds it together because it's a bit it's basically the electrons are helping hold it together, but not as a molecule. Every single one of those atoms is still independent, right? If one separated from the rest, it wouldn't compromise the whole thing. However, if you have something like isopropyl alcohol or water, right, a molecule, these are well-defined structures. you cannot remove one of these atoms from the structure without it becoming something different. So for these images, see right here, the red usually represents an oxygen, the black ones represent carbon, and white ones represent hydrogen. So this is saying three carbons. You can see one here, one there, one there. So it's like a triangle of carbons, and the one in the middle has an oxygen attached to it with a hydrogen on that. This oxygen and hydrogen is actually what an alcohol group is. All alcohols have this. So I've always thought isopropyl alcohol looked a little bit like a dog with the head and the nose. But anyway, here is an image of nickel atoms using a scanning tunneling microscope. And again, I use the word image here on purpose. It's not a picture. This isn't seeing what they actually look like. They're not purple and pink up close. Rather, right, we can use a scanning tunneling microscope to scan the surface with a very, very fine needle, very small tip. The interaction of that needle with these atoms, right, the electrons repelling against each other, allows us to map out the overall area, the force that the electron exerts against it. And from there, we can identify the overall boundaries of the atoms. Let me check. Okay. Sorry, I just got a message. I needed to make sure I didn't have something else tonight. All good. Here's one of DNA for a larger molecule. All right. Actually, what's cool here, using a scanning tunneling microscope, we can verify, right, the double helix structure of DNA. You can see the double strand and how it comes in together here, and then it goes out, and then it comes back together like that. You can kind of see the double helix shape. So, again, if you want to further take any of these notes, feel like pausing. If I don't say anything, it's probably because it's not super important. So, we have three common states of matter. I know all of you know them: solid, liquid, and gas. Right? These are our main states of matter. We have a fourth common one. Pause for a second. See if anybody can think of it. Correct, it's plasma. I am so glad you all got that. Plasma is a pretty cool state of matter. I used to work with plasma quite a bit. You can find it in nature in a few places. The sun, very, very hot flames, lightning, something called St. Elmo's fire, which often appears on the tops of ships. And one other place that you can see it in nature, although there are only certain places in the world where you can see it. If you know, leave a comment. I'll be excited to see if anybody knows. But here are a couple examples of states of matter, right? Every single piece of matter has different forms, different states. So we have solid, liquid, and gas, and the same chemical can be in those different forms. For example, easy one is water, right? Frozen water is ice. That's solid. Liquid water is water. And finally, gaseous water is steam. A quick aside, it is easy to get liquid and fluid confused and to conflate the two. Technically, gases and liquids both count as fluids in terms of dynamics and things like that. So, but yeah, here's what they look like on a small molecular view. Right, solids are typically, actually water's an exception here, but solids are typically packed in really tight. They have many different ways of forming bonds between them that hold them in close, right? But the one thing they all have in common is they are physically all packed in together and connected. They still move around, but they move around like vibrating, like this, right? They all move together. You don't have movement that doesn't occur together. So you can't just pick up a piece, one half of a solid and the other half doesn't come with it, right? With a liquid though, liquids are no longer bound together like a solid is. Instead, they're loosely attached and they can freely move around each other. So if you like grab one part of liquid, scoop it with a spoon, you pull it up, the other ones are able to freely move, so they're not so firmly attached to it that they cling onto it. Instead, they will fall off around the side and you will only remove the part you touched. Whereas, like, again, I can't pick up just the right half of my calculator and leave the left half on the table. And a gas has free movement, much like a liquid. However, right, I'm realizing that I have all this stuff explained in the next slide, so I'm just going to end up skipping over those. My apologies. You can stop and pause those if you want to write down what I'm saying right now from a written source. They are spread out. So yeah, again, solids, right, vibrating in place. They vibrate, they oscillate, they don't move around each other. The one thing I didn't really mention, they have a fixed volume and a rigid shape. A solid's volume cannot change. And typically they have a rigid shape. You might have some, right? You can squish and you can use physical force to deform a solid. Some things don't need much physical force, right? Something's soft like a putty. But without that force being applied, it's going to have a rigid shape that isn't constantly in flow. Or if you place it in a different container, it will still have the same shape. So, ice, diamonds, cork, iron, wood. You can probably just go on and on and on thinking of examples of solid matter. Most of the matter you interact with is solid. We actually have two different types of solid matter, though. We have crystalline and amorphous. Crystalline solids have what we call right, here we go, for this phrase, geometric, long range, and repeating. What does that mean? One, geometric. It has specific geometric shapes. This is just due to the stability of how things form, right? We recognize shapes because, well, one, they're pleasant to draw, they make sense having like similar numbers of sides and things like that. But we also use them in building because we've realized that they have an inherent strength from their shape. Well, molecules and atoms try to be stable. So when we look at solids, these take on geometric patterns that are recognizable in order to be stable. They also have a long-range repeating order. So the pattern repeats over and over and over again for a long time. That's a crystalline solid. So for example, salt, sodium chloride. If you pick up a grain of salt that has trillions upon trillions upon trillions of sodiums and chlorines, right? And they are in a specific order. It actually goes, it alternates sodium chloride, sodium chloride, sodium chloride. And it goes like that in every direction. Going up, sodium chloride, going away from you and towards you, sodium chloride, right? Sodium chloride, comes back this way. And it goes out in every direction until it reaches the physical edge of that grain of salt. And you can have a larger thing of salt. You can get like, look it up, you can get like large plates of salt. You can find pillars of salt, right? So it's this long-ranging, repeating order of these patterns. Whereas an amorphous solid, right, does not have a long-range repeating order. Something like rubber. Something like plastic. They just don't have this geometric shape, and you might have one that's a bit different from another part. So, right, a crystalline solid, again, will look like this. You can see this repeating structure, and it's not just something that small. It will keep repeating, going outwards, again, to the left, to the right, up and down, backwards, forwards, every direction. And amorphous solid, more like a blob. Here we go. I knew I, okay. Here's the picture of sodium and chloride. The green one is sodium. Right, the purple one is chloride. Sodium chloride, sodium chloride. Alternating in a well-ordered structure. And actually, because it's a fairly square-like structure, you will see this if you look in a salt, at a salt particle under a microscope. Very, very square edges. All right, liquid. All right, mentioned before, they move around each other. They still have a fixed volume because their molecules are in close contact. They move around each other, but they still interact with each other and hold each other together. Right? Then they really do hold each other together. That's why it hurts when you belly flop in a pool, because your force is actually pushing the water molecules apart, and it's actually overcoming this other force they're using to kind of hold each other, hold themselves together. So you can think of tons of examples of liquids, right? Water, gasoline, alcohol, mercury, coffee. You could probably go on and on coming up with more liquids. They do take the shape of their container, again, because they can move around freely. Gravity applies to them and just pushes them down into the shape of the container. That's something that solids don't do because they can't move freely. And finally, gases. Gases, like liquids, move freely, right? But they aren't held together by anything. So they're moving around like crazy. At any given moment, right? Have a gas particle like here and here and there, right? Most of a bottle of gas is going to be empty, right? With tons of space in between. Because of that, gases are compressible, right? Here is a bottle of compressed air. I could spray this for a while without it running out because there's a lot of air in here, but it's all pushed down. They're basically taking all the space in between them, right? And you push it further in and you remove that space. And it causes more pressure, right? Pressure is just the force of things bouncing off of each other, bouncing off the wall of this. And so because they pushed so much air in here, right? They pushed so much air in here that it filled up and there was barely any space around, that it's bumping around, right? Holding it, I can like feel the pressure. I can feel the force going against the side, right? it, sorry, I'm drawing a quick blank here. It's been a long day. I've been in and out of the hospital all day. But yeah, you can press them further together and it will just increase the pressure because the gas atoms and molecules are just bumping up against the side of it like crazy. So, lots of examples of gases. Usually most of the gases that you'll experience and interact with tend to be the ones you probably already know. Stuff like oxygen, helium, carbon dioxide, nitrogen, right? The noble gases are all gases, right? Other than that, there tend not to be that many good gases that you can interact with in life. Otherwise, it tend not to want to breathe things in that aren't air. Yeah, so this is an image of gases being compressible. Right? You can push a gas together, but you can't push a solid together. There's nowhere more for them to go. There's no more space for them to fill up. Here, there's more space to fill up. Same with a liquid. A liquid is not compressible. So, here's just a quick chart that has all of that. All right. Anything that's close together is incompressible. Anything far apart is compressible. Right. Definite, definite, indefinite, definite, indefinite, indefinite. So there you go. All right. Let me check where we're at with the recording time. 26 minutes. Okay. Let me... All right, so let's talk about pure substances. Or let's talk about, actually I want to go to a chart first. We're going to talk about matter, which can be broken up into two subcategories, a pure substance or a mixture. There are two kinds of pure substances, elements and compounds, and there are two types of mixtures, homogeneous and heterogeneous. So we're going to go through each of these. First, let's talk about our two big categories, pure substances and mixtures. Pure substance, one type of atom or molecule. That's it. One distinct chemical substance. Right, so remember, molecules are grouped together in specific amounts. Atoms are particles on their own. Whatever you have, when you have a big pile of it, it's all the same thing when you look at it on a small scale. That's what a pure substance is. A mixture is two or more things combined. The proportions can be variable. Those don't really matter, right? This can be a literal thing. For example, in my hand. A literal thing in terms of like, just something you can physically see. I have candy corn, right? I can see the different components, the yellow, orange, and white. See your car going off. I'm just going to make sure that's not mine. All right, that is somebody else's problem. You can see the orange, you can see the yellow, you can see the white. You can see a physical difference between the different parts of this. That's a mixture. So let's talk about our pure substances. First, let's talk about elements. An element is a pure substance that cannot be broken down into a simpler substance. What do I mean by that? You can't use chemistry to make it into something simpler. For example, water. Not as an example of an element. Water is not an element. It can be broken down into something simpler. If you take a battery and two sticks of graphite you can attach the graphite to the battery, like a 9-volt or something, and dip it in water. That will cause a chemical reaction which will break down the water and turn it into hydrogen and oxygen. In that, you're breaking down a molecule, a compound rather, into its individual elements. That is something that can be broken down. But if I have this aluminum can here, it's just aluminum. I can't break it down into anything else. Well, technically, anytime you see aluminum, the very, very, very surface layer is aluminum oxide. It's aluminum reacted with oxygen. Anytime it gets exposed to air, it reacts with oxygen, and it does that, just forms literally a single layer. So if I grabbed a knife and I scratched away at this, I could expose the aluminum underneath, but there's really barely a difference. It's slightly shinier. All right. So another way of looking at an element, anything on the periodic table. So let's talk about helium. Helium is another pure substance. Oh, sorry, we're not really going to talk about it. I was just giving an example of a pure substance. Helium. I am fairly tired from being back and forth and everything, so please forgive me. Let's talk about compounds. A compound is two or more elements in a fixed, definite proportion. Fixed and definite. So, sodium chloride is a compound. We have two elements, sodium and chlorine. They're in a fixed, definite proportion. You always get one sodium for every one chlorine. Water is another example of a fixed, definite proportion. You have two elements. You have hydrogen and you have oxygen. And you have a fixed, definite proportion. You have two hydrogens and one oxygen, and every single water is like that. Right. The other example I have here is sugar. Right? I'm sure most of you can tell me, well, at least most of you should be able to tell me the chemical formula of sugar. I know you have to learn it in biology. So as a quick refresher, it is C6H12O6. All right, for glucose. Then we have, again, the other idea, compounds can be decomposed into similar substances. We can break them down. I mentioned you can break down water into hydrogen and oxygen using electricity. Right, get something like calcium carbonate, and you can break it down. Right, limestone can react to get broken down into its other components. Right, so again, my example here is just water. I already mentioned it, but two hydrogens, one oxygen. And normally I would use this going through and pausing, but I mean, you can pause the video, so you can stop me for as much time as you need. So, if matter has two types of atoms, it might be a pure substance. Why did I put this in all caps? That's obnoxious. Or it might be a mixture. Right? If it's a pure substance, it's a compound. And those are ones that are chemically bonded together. They're physically connected. However, a mixture is different substances that are not chemically bonded, They're just physically combined. So try to think of more examples of mixtures, right? And again, it can be something more complex, like lemonade, or it can be something like trail mix. So here's some examples of mixture. Air. Air is mostly nitrogen, but it has some oxygen. It is, and some carbon dioxide, argon, and some other gases as well. Right, and then we look at salt water. It's salt and water. If we're talking about the seawater in the ocean, right, well, it's got fish in it. They're a piece of matter. It has kelp and plants, unfortunately trash, sand, dirt, random goos, right? All sorts of things that you can find in seawater. So it is a mixture. And actually, we have two kinds of mixtures. Homogeneous or heterogeneous. Homogeneous means that everything looks the same. Everything looks the same, right? Not just looks the same, but like it's uniform throughout. Usually in a homogeneous mixture, you can't separate one part of the mixture from another. They might not be chemically bonded, but you can't separate them. An example of this again would be lemonade. Feel free to let me know, beyond boiling the water out, what you would do to, let's say you made one from a mix, separate the lemonade powder from the water again. You can do your best. But I imagine all of you are capable of separating red M&Ms from blue M&Ms. Right? Even if they're all red, that's still a heterogeneous mixture because they're not connected. So, elements, periodic table. Compounds, multiple things from the periodic table together, chemically bonded. Mixtures. Homogeneous, look for something that you can't tell the difference of one part from another. And heterogeneous, look for something where you can. Oil and water is one of those classic examples because oil is hydrophobic. It repels water, and so they won't combine. So here is a quick summary of all of that. Did I? Genius. There we go. All right, I don't really need to pause because you can pause. My apologies. I'll just keep going and not waste our time. So we do have a little bit of time left, and I would like to go over the answers for the classification of matter worksheet I had given you previously, which I don't believe I had gone over with this class. Oh, did I? You know what? I think... Okay. I'm good. So, because we're getting somewhat short on time, I will actually pull up the answer key. Classification of matter. Right, elements. These are ones that we find just on the periodic table, mostly, and then graphite. I'll talk about that. So, gold, silver, oxygen, sulfur, hydrogen, all of those are directly on the periodic table. Then we have graphite. Graphite is one of the two pure forms of carbon, the other being diamonds. I know I've mentioned several times that graphite was on the periodic table. I was hoping you would also, or that graphite is just carbon. I was also hoping that you would look it up if you didn't know. Some compounds. Water, it's one thing, H2O. Carbon dioxide, CO2. Calcite is a bit trickier, right? I was hoping, again, you would look that up. Calcium carbonate, CaCO3. Mustard gas is one specific chemical. Sucrose is a sugar. Sodium chloride, salt, right? One compound. Right, then we get into our mixtures. Homogeneous mixtures include yellow mustard, right? You can't really tell one part of yellow mustard from another. You can shake it around, but you can't really separate it. Clean air. Clean natural air is homogeneous, right? You can't separate one part of the air out. You know, without using chemical kind of intervention to do it, you can't like use a physical means to be like, all right, I'm gonna put the oxygen over here and the nitrogen over here. Right? We have salt water, brass, coffee, and rubbing alcohol, all mixtures. Rubbing alcohol is isopropyl alcohol. Isopropyl alcohol itself is a compound, but rubbing alcohol is usually 70% isopropyl, 30% water. Brass here is a mixture, and that might seem confusing, but that's because it's something called an alloy. Alloys are mixtures of metals. Sometimes the combination of one or more metals can actually be a compound, but most of the time it's a mixture. And that's actually because it doesn't have to be in a definite proportion. So if I have a little bit, so if I have slight proportions for my brass, so let's say I add more zinc to it, right? Adding more zinc can actually maybe make it stronger, but it doesn't change the property significantly. So it's considered a mixture. Now we'll get into our heterogeneous mixtures. Dijon mustard. It's like the brown mustard that's a bit spicier. Well, technically spicy brown mustard and Dijon mustard are like a little bit different, but it's the spicy brown mustard that you can see darker spots in. Blood. This one seems a little odd because it looks the same, but it actually has different components. One way you can tell is you can actually separate it using force with a centrifuge. You can separate out the different parts of the blood, and if you can physically separate them, then it's not homogeneous. Dirty water, right? You can filter out the dirt. Dirty air. You can filter out the smog, the dirt, the pollution. Ground black pepper, right? You can look and you can see, right, different colored specks in pepper. And trail mix, I mean, that one's pretty obvious. It's literally a mix of various things that you can see all together. So that's heterogeneous mixture. And this is just a rehash of the chart I have in your slides. All right. With that, I think I will call it a day. Please let me know if you have any questions. Please comment. And I hope to see you all soon. Bye.